Imagine you're capable of travelling distances in excess of 1,000 kilometres, diving to depths of up to 1,000 metres, and your body is up to 7 metres wide. It sounds pretty impressive, doesn't it? So then would you be surprised to hear that it's the smallest creatures on Earth that drive your movements? Well, like whales, this is the case for manta rays. They are the largest known species of rays on Earth, but they feed on the smallest of organisms, zooplankton, the microscopic drifting animals in our oceans. And lucky for us, manta rays aggregate to feed at predictable locations. So you can use these sites to sample the food environment to understand what zooplankton they target, how concentrated it needs to be for the rays to start feeding, and what feeding strategies they use to maximise their food intake. But my research is discovering that these are not the only small animals responsible for the movements of these large rays. Manta rays are frequently observed attending cleaning stations in rocky or reef environments. Cleaning stations are like day spas on the reef. Here, cleaners attend to visiting clients to remove parasites and clean skin tissue, and it's a classic example of mutualism, whereby both species benefit from the relationship. The cleaner gets a meal, and the client has parasites removed that may have otherwise negatively impacted their health. Another characteristic about manta rays is that they have a unique spot pattern on their bellies, which allows us to distinguish between individuals and track them over time. It's like a fingerprint. And at most locations where manta rays are seen around the world, scientists or citizen scientists have been collecting photographs and cataloguing these animals for a number of years. So these databases can give us information about distribution and population dynamics, and I was able to use sightings of the same individuals to update our knowledge of their long-distance movements. But on a broader scale, I wondered if we could also use these databases at the population level to look at whether unique markings are more similar within populations of related animals than between separate populations. So the broad focus of my thesis is the spatial ecology of manta rays. How far do they move? What food environment drives their movements? And what habitats do they use? And can we use their unique markings to define separate geographical populations globally? Well, happily, we can now tick off some of these goals. We know that they can move distances of over 1,000 kilometres, and that they'll feed when zooplankton reaches a certain density in surface waters, and this is often tidally driven. We know cleaning stations are an important place for them to visit in reef environments, and it's likely the density and abundance of cleaner wrasse at these sites that determine their preference to return to the same places again and again. And finally, we have early results that suggest we might be able to determine where an animal is from just by looking at its unique markings. And these markings can help us understand the connectivity between populations of these large, highly mobile and charismatic rays. Thank you.